Section: Introduction. We're going to delve into the world of machine translation, MT, which primarily uses transformer encoder-decoder structures, as seen in models like NLLB 200, M2M100, BIBERT, and MT5. Recently, there's been a surge of interest in large language models, LLMs, that only use decoders, such as the GPT series, Mistral, Llama, Falcon, and others. These models have shown great potential in various natural language processing tasks, including translation. However, smaller LLMs, with 7 billion or 13 billion parameters, don't perform as well as traditional translation models. Some researchers have tried to improve these smaller LLMs, but the results have been modest, mainly because these models are usually trained on English-centric datasets, which limits their linguistic diversity. To address this, we've introduced ALMA models. These models are first fine-tuned with a large amount of monolingual data in various languages to improve their multilingual understanding. Then, they're fine-tuned again with a small amount of high-quality parallel data to guide the model towards generating translations. This method has allowed ALMA models to outperform all previous moderate-sized LLMs and even GPT 3.5 in translation tasks. However, they still don't perform as well as leading translation models like GPT-4 and winners of the WMT competition. In our study, we've tried to close this gap by further fine-tuning ALMA models with our new training method, Contrastive Preference Optimization, CPO, and minimal costs. We've named the fine-tuned model ALMA-R. CPO aims to address two main limitations of the previous fine-tuning method, supervised fine-tuning, SFT. Firstly, SFT's method of minimizing the difference between predicted outputs and gold standard references inherently limits model performance to the quality of the training data. This is a significant limitation, as even human-written data, which is usually considered high quality, can have quality issues. For example, some strong translation models can produce translations that are better than the gold reference. Secondly, SFT doesn't have a mechanism to prevent the model from making mistakes in translations. While strong translation models can produce high-quality translations, they sometimes make minor errors, such as leaving out parts of the translation. It's essential to prevent the production of these nearly perfect but ultimately flawed translations. To overcome these issues, we've introduced CPO to train the ALMA model using specially curated preference data. After CPO training, the ALMA-R model shows significant improvements, achieving performance levels that match or even surpass those of GPT-4 and WMT competition winners. Our main contributions are as follows. 1. We conducted a detailed analysis of the training data, Flores 200 data, used by the ALMA model. We carefully compared the quality of the reference translations with those generated by strong translation models. Our findings show that, in many cases, the quality of human-written parallel data is even lower than that of system-generated translations. This insight suggests that training models solely to replicate reference translations may not be the most effective approach, and reliance on reference-based evaluation could be flawed. 2. We introduced Contrastive Preference Optimization, which offers advantages in terms of memory efficiency, speed, and, crucially, enhanced effectiveness in improving translation quality. CPO breaks the bottleneck inherent in SFT's reference mimicking learning process and pushes the performance boundary of models that have reached saturation through SFT training. The importance of target references in machine translation tasks cannot be overstated. The training model for the machine translation task heavily relies on the quality of the reference because the goal is to minimize the difference between the predicted outputs and the gold reference. However, the accuracy of these evaluations can be compromised by substandard references. Recent research has started to assess the quality of parallel datasets, indicating that target references may not always represent the highest quality. To thoroughly assess the quality of both the gold standard references and the outputs from contemporary high-performance translation models, we propose evaluating these outputs using reference-free evaluation frameworks. We scrutinize the translation outputs from ALMA 13b LoRa, as well as zero-shot translations from the most recent GPT-4. To assess the quality of these outputs, we use two of the latest and largest reference-free models, each with a 10 billion parameter size and demonstrating a very high correlation with human judgments. These models are Unbabel, Comet-Kiwi.XXL, referred to as Kiwi XXL, and Unbabel X Comet XXL, referred to as XCOMET. We use the high-quality and human-written Flores 200 dataset, which includes both development and test data, to compare the gold references with the outputs generated by the models. We used ALMA 13b LoRa and GPT-4 to perform translations across 5 English-centric language pairs. Our findings show that translations produced by advanced models can sometimes surpass the quality of gold standard references. This raises the question of how to effectively use such data. A straightforward approach would involve fine-tuning the model using the source and the superior translations as references. However, this doesn't equip the model with the ability to identify and avoid generating suboptimal translations. This situation motivates us to develop a new training objective, which aims to instruct the model in prioritizing the generation of higher quality translations and rejecting lesser ones. This objective moves beyond the traditional focus on merely minimizing cross-entropy loss towards the reference. Section Summary. In this section, the authors introduce ALMA models, which fine-tune decoder-only large language models, LLMs, with extensive monolingual data in various languages to enhance their multilingual comprehension, and then supervised fine-tune, SFT, with small but high-quality parallel data to improve translation generation. They address the limitations of SFT by proposing Contrastive Preference Optimization, CPO, a novel training method that uses specially curated preference data to train the ALMA model. The results show that ALMA-R, the fine-tuned model using CPO, achieves performance levels that match or surpass those of GPT-4 and WMT competition winners. Section: Contrastive Preference Optimization. In this section, we introduce a new method for learning preferences, which we call Contrastive Preference Optimization, CPO. This technique is designed to help the model learn to generate better translations and reject worse ones, even if those worse translations are still of high quality but not perfect. To understand CPO, let's first look at Direct Preference Optimization, DPO, a more straightforward optimization objective used in reinforcement learning from human feedback. Suppose we have a set of original sentences, along with preferred translations and less preferred ones. We can create a static dataset of comparisons. The loss function for DPO is built as a maximum likelihood objective for a policy that's been parameterized. This policy is influenced by a pre-trained language model, a sigmoid function, and a hyperparameter. DPO training can be done in a supervised fine-tuning style, as it relies solely on labeled preference data and doesn't need interaction between agents and their environment. However, DPO has some drawbacks. It requires double the memory capacity to store both the parameterized policy and the reference policy, and it also doubles the processing time because the model has to be run sequentially for two policies. To address these issues, we introduce Contrastive Preference Optimization. We start by setting an ideal policy that perfectly matches the true data distribution of the preferred data. For any given data point from the dataset, certain conditions hold true. This is different from the usual approach of assigning the initial pre-trained model checkpoint. This change is possible because the main role of the ideal policy is to prevent deviation from the original model, and our approach aligns with this goal, keeping the model close to the ideal preferred model. As a result, the predictions for preferred data don't need to be reweighted by the reference model, and the equation can be reformulated. However, the ideal model is unreachable, but we can approximate the optimization. After expanding the sigmoid function and removing the non-parameterized term, the loss becomes something else. Considering certain conditions, the loss can be upper bounded. By restructuring the loss into a sigmoid function, we derive our new preference learning objective without computing the unreachable ideal model by minimizing the upper bound of the equation. Our approach also includes a straightforward signal to guide the learnable policy towards the preferred data distribution. Specifically, we incorporate a log likelihood supervised fine-tuning loss applied to the preferred data. By combining these equations, our CPO loss is finally formulated. The transition from DPO to CPO resolves issues of memory and speed inefficiency. This efficiency is achieved as CPO only requires the storage and processing of one policy, so CPO facilitates preference learning with the same space and time complexity as common supervised fine-tuning methods. We also show the significantly better performance of CPO compared to DPO in a later section. We also describe the construction of our preference data. This dataset is developed using the Flores 200 data and includes the same language pairs as discussed earlier. For each language pair, the dataset includes 2009 parallel sentences. For a given original sentence, whether translated from or to English, we use both GPT-4 and ALMA 13b LoRa to generate respective translations. Together with the original target reference, this forms a triplet, representing 3 different translation outputs for the input. The reference-free evaluation models QE-XXL and XCOMET are then used to score these translations, with the average scores represented. The highest scoring translation is labeled as the preferred translation, and the lowest scoring as the dis-preferred translation. Translations with intermediate scores are not considered. It's important to note that even the dis-preferred translations may be of high quality. The term dis-preferred indicates that there is still room for improvement, perhaps through the addition of minor details. This approach of using high-quality but not flawless translations as dis-preferred data helps in training the model to refine details and achieve perfection in generated translations. Section Summary. In this section, the authors introduce a new preference learning technique called Contrastive Preference Optimization, CPO, which aims to guide the model in generating better translations while also learning to reject worse ones. They address the memory and speed inefficiencies of the previous method, Direct Preference Optimization, DPO, by formulating the CPO objective to only require the storage and processing of one policy, resulting in improved efficiency. The authors also describe the construction of their preference data using triplet preferences, where even the dis-preferred translations may be of high quality, allowing the model to refine details and improve translation quality. Section: Experiments. In this section, we'll discuss our experiments, the data we used, our training setup, the baselines we compared against, and the results we obtained. We focused on 10 translation directions in our study, including Czech to English, German to English, Icelandic to English, Chinese to English, and Russian to English. We built on the insights from the ALMA models, which showed that a small amount of high-quality data can produce impressive translation results. Our training dataset is even more compact, derived from the Flores 200 dataset, which was also used in training the ALMA models. This resulted in a total of around 56,000 paired sentences in 57 different translation directions. In addition to this, our dataset includes 1,000 human-labeled preference data, which contains preferred and non-preferred translations along with human preference. However, this human-labeled data is only available for 2 translation directions, English to Chinese and English to German. More details about the composition and influence of this human-labeled data can be found in the appendix. Our main focus is on the test set drawn from the WMT-21 for Icelandic and WMT-22 for other languages. We also conducted additional experiments evaluating models on WMT-23, covering 6 directions: German to English, Chinese to English, and Russian to English. We trained our model in a many-to-many multilingual machine translation manner, starting with the ALMA 13b LoRa model as the initial checkpoint. During the training phase, we focused exclusively on updating the LoRa weights of the model. These weights have a rank of 16 and add only 12 million parameters to the original 13 billion size of the model. We followed the default value of 0.1 as suggested by previous research. The fine-tuning process involved a batch size of 128, a warm-up ratio of 0.01, spanning a single epoch, and accommodating sequences with a maximum length of 512 tokens. To optimize training efficiency, we integrated a specific tool. We compared our model against the strongest translation models, including ALMA 13B LoRa, Tower Instruct, and the latest GPT-4 model. We also compared our results with the winners of the WMT competition, which represent the highest standard of translation models within the competition. We also compared our model against different training objectives. Since our model is designed to steer learning towards preferred data, we compared its performance against directly supervised fine-tuning, SFT, on the same preferred dataset. We also compared our model against the Differential Preference Optimization, DPO, as our model is an evolution of DPO. Our results showed that our model, with the incorporation of CPO, significantly enhances its capabilities, bringing its performance to a level that is comparable to or even surpasses that of GPT-4 and WMT winners. For example, our model achieved an average score of 85.74 on Kiwi XXL and 94.05 on XCOMET for English to other languages translations. These scores outperform GPT-4 and the WMT winners. Additionally, our model outperforms Instruct Tower across all translation directions. When comparing with SFT and DPO, we found that SFT on preferred data slightly enhances the model's translation capability for other languages to English, and results in a slight deterioration for English to other languages. Similarly, DPO slightly decreases model performance. In contrast, our model demonstrates significant improvements across all translation directions. Section summary. The experiments in the paper focus on 10 translation directions, using a compact training dataset derived from the Flores 200 dataset. The dataset includes both preference data assessed by large evaluation models and 1K internal human-labeled preference data. The models are trained using ALMA 13B LoRa as the initial checkpoint and fine-tuned with a batch size of 128 and a maximum sequence length of 512 tokens. The results show that the incorporation of CPO significantly enhances the performance of the ALMA models, surpassing GPT-4 and the WMT competition winners in certain translation directions. Additionally, comparing with SFT and DPO, CPO demonstrates significant improvements across all translation directions. Section WMT 23 results. In the WMT 23 results, we found that our model, ALMA 13BR, outperformed other similar-sized language learning models like ALMA 13B LoRa and Tower Instruct. It also matched or even surpassed the performance of previous WMT winners. We've included detailed results for each direction in the appendix due to space limitations. We conducted our analysis using the WMT 21 and WMT 22 test datasets. One question we wanted to answer was whether the improved translation scores were genuinely better or if they were just more aligned with the evaluation model's preferences. We looked at this question from two angles. First, we checked if training a model on data preferred by a specific metric, like Kiwi XXL, would consistently improve performance across other metrics. We did this by recreating the preference data using only Kiwi XXL or XCOMET and retraining the ALMA 13B LoRa model. The results showed no significant bias towards the metric used for selecting preferred data. We saw similar improvements across all metrics, regardless of the specific metric used to select the preferred data. Second, we wondered if training on metric preferred data always leads to better scores on that metric, regardless of the method we use. However, we found that this isn't always the case. For example, using SFT on preferred data actually resulted in lower performance across all three metrics. This suggests that using reference-free models like Kiwi XXL and XCOMET for constructing preference data and for evaluation is a robust and valid approach, free from bias. We also conducted an ablation study to understand the importance of different components of our model. The CPO loss function, for instance, has two parts, one for preference learning and another to ensure the model doesn't deviate too much from the preferred data distribution. We found that using both parts together gives the best performance, while leaving out either one leads to a drop in performance. We also looked at the importance of the data generated by both ALMA and GPT-4 in our preference data selection process. We found that excluding data from either system leads to a significant drop in performance, showing that both systems contribute to improving the model's performance. Finally, we investigated whether the quality of DIS-preferred data, which comes from strong translation models but receives the lowest scores, significantly impacts model performance. We created a new set of preference data where the DIS-preferred translations were artificially generated, rather than being naturally derived high-quality translations. We found that using these artificially noised DIS-preferred data led to a significant drop in performance across all metrics and both translation directions. This highlights the importance of the quality of DIS-preferred data in improving translation performance.